Okay, let's see how to deploy the vector control algorithm and make this motor run. So first we have to connect the Hall output from the motor, Hall sensor reading from the motor to the panel. So make sure you have a ridge that has to mate with this connector. You will hear a click sound, and for deploying this algorithm into the C2000, you have to connect a USB terminal to the PC. Also make sure that this phase sequence is in the order which is shown here. The black has to be connected with the blue, and red has to be connected with the green, and yellow has to be connected with the yellow. So to deploy our vector control algorithm and to operate the motor, we have provided a set of MATLAB files. So go to this PC in the local disk D under MCOG folder. So since we are using PMSM, you have to open the FOC and .slx file or the Simulink files. The vector control host is what you use as a control panel to change the reference speed, which has a slider and everything. And this MCB stands for motor control block set for permanent magnet synchronous motor, and FOC, since it is Hall based, it is Hall. And this is our processor's identification. Okay, so you have to open this SLX, and do not open this cache file. This is auto generated file. So once you open it, you will be greeted with this. So all the code for the Clark Park transformation, everything resides here. There are two loops, current loop, speed loop, everything sits here. So if you want to change the PI control, PI gains or something, you go to the speed control, and here you can change the KP and KI. And in current control, you can go into the ID PI gains and IQ PI gains. You can change this. Okay, so make sure you have connected the USB to the PC, and in MATLAB go to the hardware tab. There is a button called build and deploy. Do not press build. Build means it will just compile the this GUI into C code, and it will not transfer it to the processor. So you have to build, deploy and start. You have to press this button. While it is deploying, you can see the RX and TX illuminated here. So after successful completion, this heartbeat will blink. Actually, you can see what makes this LED blink here. In the MCB PMSM Hall, this file, this is the actual file we will deploy to the hardware. You can see there is a block called LED heartbeat. Once you go in, there is a constant block which has sample time of 0.5. That means it is, we are turning on the GPIO pin for on for 0.5 seconds and off for 0.5 seconds. So this constant with a sample time of 0.5 is actually pulling up the pin and pulling down the pin of GPIO 123. That's what makes the LED blink there. So after you have completed the deploying process, you have to open this vector control host, which is your operator panel. So once you open it, it will look like this, which has a slider here. You can change the reference speed, and you have an inverter enable disable. So this is what is actually turning on the motor and turning off the motor. And there is a scope. You can monitor two signals at a time. So if you want to monitor IDIQ, you have to click this, and IAIB. So but we want to mainly monitor the speed reference, and speed feedback means what we are measuring from the Hall. We are calculating the speed from the Hall transition. We are getting the speed. So that is speed feedback. Okay, you press on, you can double click on this scope to open this, and right now we have selected speed reference and speed feedback as the signals to monitor. So this is what the processor will also send from there. Okay, before you do that, you have to make sure if any of the Hall sensor is giving invalid signals, we can make a quick check with this. So you press on the simulation and you run like any other Simulink model. Press on the run. You have to physically rotate the shaft like this in the positive direction to so if you rotate in the positive direction, the Hall transition will change and the controller will calculate some speed and it will be displayed here. positive direction is our clockwise direction and the negative direction is our anti-clockwise direction. So if you rotate in anti-clockwise and you see a negative, that means halls are working properly. There is a rough gut check. So if any of the hall sensor is not wired properly, you will not get this. Move the slider to the lowest available, which is 150 rpm. We have given 150 rpm because at very low speed at very low speed the hall transitions are sparse and the speed estimation from the halls will not be that accurate. So the minimum speed we have provided is 150 rpm and we have limited the maximum speed 1500, even though this motor can go up to 1800. Okay, let's turn it on. Okay, so let's now increase the reference speed here. You could see the motor actually following along. Now let's increase the time span, go to the time and increase the time span to about 6 or 7 seconds. The yellow is what we are setting in the slider and the blue is what the motor is actually doing. You could see the motor overshoot, undershoots, it's trying to follow what we are giving from the slider. Okay, let's go to the maximum speed. And at no load it will draw about 1.6 amps, as you can see here.